all that is to say is, based on Tuesday when I showed you Ampere's law, that was the last piece of new physics that'll be on the exam. So that gives you 9 days for it to sink in. Obviously today is one of those days. You'll see lots of good examples for today. You have tomorrow at the MC. I know you'll get lots of help and questions there. And before I pull down the overhead, just wanted to remind you about Don's review then on Sunday. And so Sunday, right here in this room, 1 o'clock, Don will do a review. He did want me to share with you that he's going to start actually in the higher chapters, 29 and 30, with the magnetism. So he's going to start with the magnetism and kind of do those, part because they are a little bit harder, and he wants to make sure you are fresh when you hear all this stuff. But the other big part of it is because the other half, the chapters 27 and 28, are the easier stuff, but they're also the stuff that many of you are also doing in your circuits class. And so many of you probably won't feel like, well, I think I got a handle on that pretty good, and then you can just leave after that. So that's the purpose of the order of his approach. All right, well, with all that said, let's go ahead and get started. Oh, well, happy Electron Day, right? Or, right, oh, Halloween, right? Okay, yeah. But it's 10:31.
In a few minutes, 9/11.
Oh, and we'll be at 9/11. There we go. All right. Oh, set my alarm. No, okay. But yes, we'll have electron moment. Yeah, right. Yeah. All right. So, going back to this picture of Ampere's law, and I forget which diagram it was, but we did just kind of that first step to get us familiar with the terms in Ampere's law. It was this one here. And we said, let's look at the current. And so let me put on the board Ampere's law and run through this again here. And so the integral over a closed loop equals mu naught times I, where I is the current enclosed inside. And so let me just mention these again. Maybe right next to it, I will put what we had on Tuesday, and that was, remember, this idea is similar to Gauss's law. Gauss's law, we did an integral. We looked at what sources were on the inside. In each case, we had a closed integral. Something slightly different was this was an integral over the surface, so it was a flux integral. And this one is an integral along a path, a curved, so it's a line integral. So in that sense, there's a difference. But other than that, they are very similar. And the logic that we use to solve them is very similar. So, wow, pen's low. All right, well, skip that color here for today. But let's go through all of this and apply this again to this long straight wire. So in the last 10 minutes, you'll recall, I said, hey, let's do one quick calculation to get us started. And we did this first Amperean loop. So going back to this picture, we have a current going through here. Let's draw Amperean loop number 1. And our logic was to first do the dot product. And so if you do the dot product, you'll get an integral that looks something like this. And I guess it needs to be a closed line, a closed loop. And our logic was that, okay, let's look at B, let's look at theta. And as we said last time, if you think about B, and I use this pipe over here as an example, if this is the current, and you were to take a couple steps back, as I am this distance away, then there would be a magnetic field at this point created from the current there. If I was over here, same distance away, the sources causing the magnetic field would look exactly the same to me. And that because of that, I would come to the conclusion that the B must be exactly the same. Same magnitude, same direction. Even if I don't know what that magnitude or that direction is, at least I would conclude it's the same. And so our argument, like we had done in the past, was using symmetry to say, well, we don't maybe know the value of the magnetic field. In fact, that's what we want to find, but at least we can pull it out of the integral. We know that much. It's going to be a constant. And so there is the first step. The other step is to say, let's look at this angle between the B and the ds. And in that case, we went back to the B-ups of art. We had done this before. Maybe it's worth reviewing, but take that right hand. I think we call this right hand rule number 2, but not worrying about the numbers. We said grab the, no 3, this was 3, huh? Grab the wire, put your thumb in the direction of the current, and your fingers will indicate the direction of the field. And so there'll be little loops around there. Or we could go back to cross product. If we think about the current coming out here, and we go a little distance dr, we would get out of the board for the ds, cross towards dr, and get up. But in this little area then, the magnetic field would be up. In this little area, the magnetic field would be down. All the way around that loop, what we do know is the angle is 0, meaning that the angle of the magnetic field and the angle of the tangential to the loop are in the same direction. That means the angle between them is 0. And so we did a quick integral that came out to be equals to 2 pi r. The other side of the equation, in this case, was the easiest of all. This is, well, how much current goes through that loop. And as you guys told me last time, all of it, so this would just be mu naught I. And so my I on the inside would become I total. And so we finished the day by saying this then is the magnetic field from one single long straight wire. Well, let's continue, because then I said, well, what about on the inside? And we didn't quite have enough time, so you remember we left a few minutes early, and that's why I got like 7 emails yesterday saying, hey, I heard Physics 122 is an easy class and I want to take it next year. You always let your class go early. No, obviously. Yeah. But back to this one then. Let's apply this again to say, what is Ampere's law when we apply this to loop number 2? And so here's our Ampean loop yet a second time. And so taking a close look at that, we can hopefully do that same logic. First thing to do is to take the dot product and to look carefully at the symmetry of the problem. Now this time, but like Gauss's law, it was very powerful to go inside a charged object to do Gauss's law. This will be very useful to go inside the current to do Ampere's law. But the real key is about symmetry. So imagine yourself standing inside, maybe right here. And so maybe the center of the wire I will put right here at the faucet. Let me stand back a little bit and realize then that I am in the wire, so the edge of the wire is some distance out there circling around. But I hope you can see that if I were to stand here and look at the center of the wire, I would have current all around me. And if I would move over to here, I again would have current all around me. But that distribution of current would look the same here as here. And because the magnetic field is created from that current, I would come to the conclusion that the magnetic field would be the same value everywhere on there. Yeah.
Do we actually know the permittivity, or what was it again, the permeability of free space constant?
Do we know this? Yeah. That number is 4 pi times 10 to the minus 7. Yeah. Oh, and I guess we got some units here, so the units would be a Tesla meter per amp. Yeah. And most definitely, you'll need that. In fact, we'll use that number real soon here, because after I do a couple more examples of Ampere's law and show it to you, let me jump into the back of the book and do some calculations. Yeah.
Could you explain what would happen if we put a test charge outside of the wire versus inside the wire and see what would happen to it, where it would go?
Oh, now, okay. If you're saying there's a force on a charge, going back a chapter, that's going to be the force on it. Okay, fair enough. So now, though, I have to ask not only what is the charge you're talking about, but what is its velocity, its magnitude, and its direction.
So if it's inside the wire,
So if it's inside the wire, going which way?
with the current.
With the current? With the current. Well, I guess I have not finished the direction here in this calculation, but I'll go ahead and chase to that since you're asking about it. But this magnetic field would be in this direction because of my right-hand rule, and so I'm going to get a field going this way. So I guess what am I saying here? So a charge from the current itself coming out of the board, right? There's V. B is up. Now V cross B would be that. If these are positive particles, they would be inward, which if we're talking about current going this way, then they are positive particles. I know that most wires, this is an electron, so if we switch this, this is probably an electron going the other way, and so an electron. But so what did I come up with? So there'd be a force inward. So I don't know, is that what you were saying? Yeah. But maybe that hopefully doesn't surprise you, because if I were to have said the same thing out here, which I think was your question, what if there was something outside? So if there was a positive particle on the outside going this way, wouldn't we have done the same thing? We would have said, okay, the charge is moving this way, the field is up, V cross B is then towards the wire. And isn't that what we did at the end of the class? Didn't we have two wires? And we said if you had wire 1 and wire 2, the first wire would make a magnetic field, and then you would have moving charges near that, and they would pull together. And so we did have a little equation that said what would happen with two wires with the current in the same direction. They would pull together. All right, now back to this calculation of what is the magnetic field when you're on the inside. I can then pull the B out in front, was my logic here of saying, hey, let's look at the symmetry. Also, same idea for the angle, which is kind of what your question was related. What direction is all of the magnetic field? And your question went a little further on what force is on there. But if I were again to look at some of this stuff here and say, all right, what direction is it? You could argue that, all right, the little chunk here would make the field this way, a little chunk here would actually make it opposite, but there's more chunks on this side than this side, so you might say right here, all these chunks going that way would make the magnetic field that way. All the chunks on this side would make the magnetic field the other direction. I've got so many more on that side that I'm quite sure what's going to happen is it's going to be a net effect in this direction. I suppose you could even jump all the way to Ampere's law. I should have put inside here to be a little more clear, because as Gauss's law, and we had this discussion back in 24, what's kind of nice about it is even though there might be charges on the outside, and just like Ampere's law, even though there might be current outside of that loop, they balance each other off. And so everything outside of this Gaussian loop, these guys over here would make a magnetic field up. These guys over here would make a magnetic field down. There's less of them here, but they are closer, and the two balance off, just like our argument was for Gauss's law way back a few chapters ago, that you definitely could have charges outside of your surface, but they're not needed to do the calculation because they balance off. And that's what we would have here. And so if you take that in the right-hand rule, you would then say, well, I have then a loop, and the current is going this way, and my fingers curl in this direction. Well, the point I'm trying to get at is no matter how you want to look at it, Biot-Savart or Ampere's law or this right-hand rule trick I talked to you about, you're going to get the direction of the field to say it is cosine of 0 degrees. That's the point for this case. And then you have the integral, which just comes out to be 2 pi r. And so the inside loop actually really was exactly the same logic with the same answer and the outside loop. I guess the only difference we mean is on the inside we are looking at r, little r, less than big R being the radius of the wire. Whereas this first time we were talking about an equation that was valid when you were outside the wire. And of course the real difference comes on the right hand side of the equation when you ask then how much current do you have going through your Amperean loop. And some of you already said it today, but I know many of you said it on Tuesday. You said, oh wait, for the inside loop, does all the current go through there? No. And so now we need to figure out how much. Which then brings up the question, well, how is the current distributed? Is it evenly distributed? If it is, it's going to be a fairly easy calculation. If it's not, well, then I guess we have to know how it is distributed, and we have to figure that out. Yeah.
You mentioned a force towards the center of the wire.
Yeah.
Is that contributing to this?
There.
The charge distribution within the wire.
Yes, absolutely. So it may not actually be uniformly distributed, but remember these are a bunch of electrons. They're all negative. And these electrical ones will dominate it. So even though they might be pulled in because of their magnetic effect, they are evenly distributed based upon their electric effect. But they're also distributed based upon the atomic crystal structure of what that thing is made out of. Okay, maybe depends on, that also depends on how much effect. But the simplest case is let's ignore the effect of the lattice of the material, which is pretty reasonable for metals. Let's also ignore the pulling together because of magnetic motion here. Because remember, these aren't going very fast. They're just the drift velocities. Okay, so which is very reasonable. They're mostly dominated by the electrical repulsion between them, and because of that, they'll be roughly equally distributed. Okay, so I will take it as they are equally distributed, but at least set it up for an example problem. Hopefully, we'll do within an hour where they're not equally distributed. Okay, but let's take them as equally distributed for our first one here. So if it's equally distributed, I might say J equals a constant. Now it's been a while since we used J. What was J? Way back in chapter 27? Yeah, it's the current density. And so this is the amount of current per area. How is that current spread out? Is it evenly spread out or not? And like you asked, and let's use it, let's just say it is evenly spread out. So keeping that in mind then, if you think of the current density as a little bit of current spread out in a little bit of area, you could then get the total current by adding up the current per area over some area. In other words, J dA added up would give you the total current. And so from a calculus picture, it might look like this. If this is the wire, you would have a little current density in there. And if that's your area, dA, you take J times dA, and you get a little bit of current that is in there. And so what I'm going to do then is add that up. And if it helps, all these calculations are very similar to what we did with Gauss's law. We did the same thing with Gauss's law. Back here, we said the charge inside is the summation of a bunch of charge. And the charge inside can be distributed with some charge density, and you'd have to add it up per volume. And so the charge density times the volume would be the little charge there, and then you would add it up over the whole volume. And so I'm saying nothing new other than it's not three-dimensional, it's two-dimensional, that I'm going to add up all my areas to get the total charge inside there. And unfortunately, this is a fairly easy one, because this integral of J dA comes out to be nothing more than pulling the J out in front for the easy case where the current is evenly distributed. And so I will have a mu naught times a J times, and I'll just put capital A once I do that integral. And what is capital A? Yeah, it's area. Area of what? Okay, it's a circle, so it's pi r squared. Is it capital R squared or little r squared? Yeah, it would be little r squared. It would be the radius of the Ampere loop, which I guess in this diagram they're just pointing an r to the big one. But if you think of r as the radius of the Ampere loop and the capital R the radius of the wire, this is really where the current is, and so that's what I need to add up. Yeah.
Should those, when we did our Ampere loop on the outside of
Yeah. Over here, yeah.
maybe a capital?
Yeah, here's a good question. Back here, was this a capital R or a little r? And maybe I should have even asked it here. Was this a capital R or a little r? But you're asking this one. Capital R or little r? Well, let's see. I'm doing an integral along an Ampere loop. So this is the summation of the curve along the Ampere loop. So this is the circumference of the Ampere loop. So therefore it is little r, right? Not big R. This is not the radius or the circumference of the wire. This is the circumference of the Ampere loop. And same thing over here. This is the circumference of the Ampere wire. So little r here is correct. Little r here is correct. Little r here is correct. We don't even have a big R yet. It's coming. It's coming, but I don't see it there yet. Yeah.
I'm a little bit confused here. In
Good.
Gauss's law, we added up many shells, which is a two-dimensional thing.
Yeah.
And here we're adding up many two-dimensional things to add up to a two-dimensional thing.
We're not adding two-dimensional things. We're adding one-dimensional. Oh, no. Oh, wait.
You added up thousands of shells.
Wait.
Two-dimensional. To add up to a total volume.
No. I guess I would not phrase it that way. The last step is to add a bunch of shells to get the volume. The step before that was to add a bunch of rings to get a shell. The step before that was to add a bunch of points to get a ring. So we took points to get a ring, we added the ring to get a shell, we added the shells to get a volume. It was a three-dimensional calculation. We added chunk to get a whole volume, right? Maybe a better way of looking at it is right here. This is what I'm doing. I am adding a chunk of charge. I'm adding up a three-dimensional shaped object to get the total charge inside. Over here, I am adding up an area. I am adding up a two-dimensional chunk. The shells added up to get the volume were just the last step of what you might like to call a triple integral, but We don't use that word because our book only goes to Math 160 if you read the preface. It's your prerequisite is Math 160. You don't need triple integrals. So we won't do any triple integrals. We'll just do a single integral 3 times. That's been our answer all along. We took points and added them together to get a ring. We took a ring to add together to get a sphere. We took spheres added, or shells added together to get a sphere. That wasn't a triple integral. And I'm sure you feel a lot better about that, right? And likewise here, we're not doing a line integral. We just do a dot product and end up with a ds, and then we just, do a single integral. It's just ds, right? It's not a line integral. And then that's kind of how we've kind of avoided discussing the higher mathematics. But you guys are at that transition where it's almost getting a little silly, that's why I'm bringing it up, not to use the words line integral and flux integral and triple integrals. But that's what I would say. I think this class was the one I was saying, or was it my 121, where I said there'll be the next class where your teacher will come in and say, okay, remember all those electric and magnetic fields you learned in Physics 123, together with all that wonderful math you learned in 200, 210, and 220. Let's put them together and do some real problems. And so I keep saying for this class that let's put your physics in 102 together with your math of 150 and 160. And so you're just going to the next layer of the onion. Was that this class? Yeah, okay. And so that's where we're headed. All right, but good question. Yes, this is definitely an R, and it's a little r on both sides. And so let's keep going here. I'll maybe clear on this side over here and say, all right, let's simplify this so that we can get an equation for the magnetic field inside, which is my second example of using Ampere's law to get the magnetic field. And so, as you probably noticed, there is a pi and an r on each side. And so what I have so far is the magnetic field B is mu naught times the J times the R over the 2. And it's not a good idea to finish any problem with using symbols that weren't initiated in the problem to begin with. So the J would not be a good way to finish this problem because that's something I invented along the way. And so let's talk a little bit more about the J. The J, as we said, is the current density. And so let me replace the J with the total current spread out over the total area. And what is the total area that the current is spread out? Pi r squared. Which r? And there's your question, right? The big R. So this would be pi big R squared. That's where the big R would come into play if I looked at all the current. And that way I can write an equation for what is the magnetic field, not in terms of how much is inside the Ampere loop, but how much is total in the wire, even though it's the part that's inside the Ampere loop that I significantly care about. And so with that said, I would have a mu naught, an I, and an R over 2 pi r squared. And so here is our second neat little equation as we apply Ampere loop and say, what is the magnetic field? And in fact, if we put these two ideas together, we can say, all right, what is the magnetic field based on distance, where capital R is then the radius of the wire. And if we look at what we've come up with here, we have this inside the wire. And so this is valid for R less than capital R, little r less than capital R. And you can see then that these numbers are a constant, well, at least if our current is a constant. And so taking our current to be a constant, which we pretty much have up to this point, that's about to change after the test, and we're going to do some funner things where we let our current change with time. But for right now, our current has been a constant, and what you would have then is you have a nice linear relationship where in the center of the wire, little r is 0, you have no magnetic field, and the magnetic field gets stronger and stronger and stronger and stronger and stronger until you get all the way to where little r is now equal to big R, and in fact on that surface you will hopefully notice in this equation when little r is equal to big R they would cancel and you would end up with mu naught I over 2 pi capital R. And hopefully not a surprise, although I erased it, this equation for the inside fits with the equation that we said was for the outside. On the outside we have this mu naught I over 2 pi R again. And so using the little r as how far you away from the center of the wire, this equation would match this equation right on the boundary. And so either one are valid right on the boundary. But once we get on the outside and we apply this equation, we will see that the magnetic field tapers off with a 1 over r relationship, whereas in the wire the magnetic field increased with a linear pattern. Yeah.
So the maximum magnetic field is when now r equals big R?
Right. So if your intent was to get to the largest magnetic field, where is it? Yeah, it's right on the surface of that wire. That's where you are a nice balance between being close but not getting in so close that you now have current on left and right side of you, which tend to cancel off. That's why in the center the magnetic field is 0. If you imagine splitting this wire in half and looking at, say, this half here and doing my fingers, if I grab that wire, this half of the wire would make a magnetic field pointing up here. This half of the wire would make a magnetic field pointing down. They're equal halves. The total magnetic field you get at the center then is 0. And so again, that's why the surface is a nice balance between being close and yet not having fields start to cancel each other off. Side note in this is we, a couple chapters ago, talked about superconductivity. And we said only one of the challenges, and here's the second challenge. I mean, the one challenge we mentioned about superconductivity is it goes away after a certain temperature. So superconductivity only works below a certain temperature. As we said, above that, the atoms shake and vibrate so much that the nice little patterns that get arranged fall apart. But superconductivity falls away also when the magnetic field gets too strong. So even if you are willing to make a wire and cool it down to a low temperature and say, well, I've got a superconductor, so I'm just going to put thousands of amps through it, you still won't get a superconductor, because at some point the magnetic field will get too strong and destroy your superconductor. So the center part of it may be a superconductor, but at some point as you go out, because you have so much current, you're going to destroy your superconductivity again. So unfortunately, superconductivity has its challenges in real-world applications, because we lose it when the temperature gets above a certain point, and we also lose it when the magnetic field gets above a certain point. And that can be a big challenge, even if, like I said, we're willing to just cool the whole thing down and pay the cost of cooling it down. It's still got the magnetism challenge. Well, I'll keep going, because again, I think seeing some of these calculations are nice to see. Your author says, all right, now that we got a good idea of how to do Ampere's law and we realize the magnetic field from inside and outside a wire, let's start asking the question, how can we get the magnetic field maybe a little stronger? And I'll pass a couple of these around, but this is what we call a toroid shape. I like to call it the donut shape here, right? It's got kind of this rounded, although this one is kind of more of a rectangular cross-section, but it's got wires that loop around, but then they also loop around, making a complete circle. And what you'll hopefully see here in a minute, like I said, I'll let you kind of analyze some of these, but this can really make a strong magnetic field. Because, watch this. Let's come back to this simple wire. If I were to look at this and say, okay, how could I make a strong magnetic field? What would I need to do? Which was kind of what your question was. Where is the field the strongest? And as you look at these two equations, I think the obvious place is you're going to say, well, make the current really, really large. Okay, fair enough. How else could I do it just besides getting more and more current? Right. And let's look at a little loop again. We did a few of these before we got to Ampere's law when we did the B-ups of art. But if I put a single loop here on the board in this picture, you saw something that I hope was interesting of why the field got to be significantly strong for that loop. And I would say for a single loop. Because what you have in a single loop, something like this, if the current is going around like this, and maybe just for a mental exercise, let's just look at this little section of the wire right there. If the current is headed in this direction, and I ask myself, well, what's the magnetic field inside of that loop? Just looking at that one little chunk, let me take my right hand again. I'm going to take that thumb, I'm going to point it forward, I'm going to grab it with my right hand, and my fingers would be coming out of the whiteboard, right? If you did that anywhere else on this ring, wouldn't you get the same effect? I mean, over here, the current would be heading down, so I'd take my right hand, grab it so my thumb is down, my fingers would curl around, and I'd get out of the board. And so, whether you saw it or not, let me point it out now that what made the magnetic field significantly strong was the fact that all these little sections added together always pointed out. And so, making a strong field doesn't really happen well with wires. And in fact, the lab you do next week, you will be asked to measure the magnetic field. One of the configurations you will have is a long wire, and you will struggle a little bit with it. You will realize the field's not very strong from the wire. But other configurations will have you make circles and twists, because every time you make a little twist, it's like taking the magnetic field from that whole wire and concentrating it right there. And so the advantage of a toroid would be to say, take that little twist and put another one next to it. And so the single twist made the field stronger. A twist yet again doubles it. And a twist a third time, a fourth time. And so you can see the ones I'm passing around have thousands of little twists as they go around. Yeah.
How does the outer end relate to the north and south pole?
Well, let's see. So did I bring a ring today? I didn't quite bring a ring, but maybe I'll use this as the ring. I mean, the picture I have right in here is a ring that looks like this, and the magnetic field is pointing out. Let me turn it a little bit this way. And so here's the ring again. Maybe I'll make it more of an oval. That look like the picture? And the field right here is pointing out. Now, all we calculated was the field along the axis. But if I were to calculate it off axis, which was kind of our discussion was last time, what if you're off axis? Well, you're going to need some math, 200 and 220 for that. But if you calculate it off axis, you're going to get a field that looks like this. So on this part of my wire, this is where the flux is coming out. So I'd call that North Pole. here's where the flux is coming in, I'd call that south pole. And so that's how I'd label the poles of this little loop that has current flowing around. Yeah.
So wait, if the magnetic field is perpendicular to the electric current, doesn't mean that the loop one is just magnetic field, and because the thing is, if you go as perpendicular to the magnetic field again, loop two be an electric field. So what kind of field in the middle of the range?
Glad you asked that. Let's calculate it. Okay, let's talk about that. But let me do the easy one first before I get to loop 2 and the inside. But let's look at this. But conceptually, I just wanted to start there. Conceptually, I wanted to start with you will get a stronger field if you make loops. And so here we have a toroid. It will make strong fields. Let's get the equation for it. The toroids I passed around were one set. You guys, I think, will remember we started this a while ago with this. And I was showing you that I could make current in this coil. Now, I wouldn't call this a toroid. We'll do this next. This is what I call a solenoid. But when you plug this in and turned it on, at first, without being on, it will not hold a paper clip as you saw before. But if I turn it on, oh yeah, it'll easily hold a paper clip. Turn it off, and it will pull it down. And some of you were asking, why is the magnetic field so strong on the inside? Well, I hope I'm answering it now. It's strong on the inside because this is the place where the field from all the different pieces of the wire add together and become very strong. And so there is a strong field on the inside of all these coils, whether it be in this shape, which we're going to call a solenoid, or one of those toroid shapes. Yeah. It won't shoot it out. No. It will change the direction of the current. And so I will have this side being a north and this side being a south. And it's still a magnet. And it's still going to...
You make the current strong enough, will it shoot out?
No. Remember, okay, so let's go back to Gauss's law. If I had a positive object and I brought a neutral object nearby, and in this case, by analogy, if I have a magnet and a non-magnet, what happens? Didn't we say this induced a dipole and the neutral object was attracted? What about a negative object near a neutral? What happened there? Okay, same idea. It induced, but we still ended up with attraction. And so whether you have positive or negative, whether I have current clockwise or counterclockwise, they equally attract a neutral one. Because what's going to happen to this paper clip is if this is a south pole, the iron in the paper clip is going to twist so that this becomes a north and that becomes a south, as we saw when we did the core back. On the other hand, if I change the direction of the current, this becomes a north, this becomes a south, and then the little iron pieces in the paper clip flip around so that this becomes a south and this becomes, and either way it attracts. The only way I'm going to get it to push out, if you will, is repel, is if I actually then put something that was a magnet in here. Then it could shoot it out. Yeah. So if something was permanently magnetized. Although then I will have to be a little careful, because if I make this too strong, I may even flip the permanent magnet, right? Permanent magnets, again, are just those atoms locked harder into place. They can still flip as we as we saw. And that's why we said above a certain temperature, our material is not going to be magnetic anymore. The atoms are just hitting too hard. All right, so getting to the main point here, which is, all right, what direction, what is the strength of the magnetic field from something that looks like this? And so, let's come over here and apply Ampere's law to the toroid. And I think your author should have done a more complete picture here by saying there is really three areas we should probably discuss. We should probably ask, what is the magnetic field on the outside of the toroid? What is the magnetic field, what I will call the interior tunnel of the toroid? Not to be confused with the third one, what is the magnetic field on the inside piece, which you might call the donut hole part of it. Okay? Why don't we start with the outside here? It doesn't really show it in that picture, but if this toroid looked something like this, and then I draw an Amperean loop around it at, say, some radius r, and I apply Ampere's law to it, I would first take the dot product and then ask, like all of our ones, if you're somewhere on this Amperean loop on the outside, which he doesn't show one on the outside, but if I take one here on the outside, which, let's see, what does he label for this outside radius? C? So I'm really talking about places where R is greater than C. So on the outside of my toroid, I could at least conclude that everywhere on that Amperean loop, the magnetic field is the same value. Whether I know it or not, it's on the same value, the symmetry of it. Now, that's a little misleading, because if I'm on a loop out here, does the current distribution look the same here as when I'm here? Well, I would say if I'm right along the line of the loop, and then I get halfway between, the answer is no, it doesn't look the same. Okay, so we're going to kind of overly simplify this problem. We're going to say that these wires are so tightly wound together that you really can't get in between them. And so anywhere you go on this loop, you see the same current distribution. I know that's not completely true, but if you look at the ones I passed out, you will see how tightly wound they are. And so we're kind of close to the ideal situation, but we can never really get an ideal situation. But at least it'll make our math easy if we say everywhere along the Amperean loop, the current distribution looks the same. That is my justification for pulling the B outside of the integral. It's also my justification of why I would say the angle is 0, because as I look at all the currents here, and I step out to here, I would have things like, well, this part of the loop would make a magnetic field at this point as the current goes around this loop and then up. If I grab my right hand, the magnetic field from that little section would be pointing this way. It would be along the loop. Now the part above it would be going, say, against the loop, but the part right below it would exactly cancel it. So the stuff above and below, I don't need to pay too much attention. This one that's in here, you may say, see if I did this right. So on this one, it's pointing this way. Then on this current, it's pointing the other direction. But it's still equal, I mean, it's still opposite in this sense that it's along the loop. So the angle's still going to be 0 degrees. And in fact, if those two come out to be equal, then the field will cancel and I'll get 0. If one's stronger than the other, then I will get a value for the magnetic field. As you will soon see, they actually do cancel off and you get 0. And that's what I want you to see, because this next step really kind of gives it all away. How much current then is inside of this Amperean loop?
Same.
Right. And again, sometimes this is hard to see because you've got to see this in 3 dimensions. But if this is the Amperean loop and it makes up a plane of this whiteboard, one of these loops would be coming out, then switching over and going in, right? And so maybe in this picture it would look something like this. The current goes in to my Amperean loop, out of my Amperean loop, into my Amperean loop, out. And so for every in, isn't there an out? So what's the net current going through my Amperean surface? 0, right? And so there's the current going through my Amperean loop. It's not 0 where?
On this Ampere loop?
Now the Amperean loop I'm talking about is not in this picture.
Oh, okay.
I'm talking about an Amperean loop on the outside. Okay? So an Amperean loop on the outside, bigger than the donut. I would have wires coming out and then wires going in, and I would have just as many coming out as just as many going in. And so how much goes through the Amperean loop? 0. Which then brings me to a very easy math answer. What is the magnetic field outside of the toroid? 0. And I think that's why the author didn't bother to do it. It's so obviously 0, who needs to even discuss it? But it is a nice feature of toroids. Toroids give you no magnetic fields outside, at least in an ideal situation. You guys next week in the lab will have the privilege of actually measuring it. It's kind of fun. You take your probe and you measure the field on the outside. And you will notice it's pretty small. You won't get 0 because, you know, it's not a perfect evenly charged distribution. But it is reasonably close. In fact, your experiment looks exactly like this. You have the spring and you are going to take the slinky and wrap it around and do that. That is going to be your homemade toroid. And you are going to take your probe and you are going to start here and you're going to measure the magnetic field and you're going to get closer and closer and closer and closer and closer and closer and you're going to see 0, 0, 0, 0 and then you're going to get inside. And then hopefully you'll be pleasantly surprised what happens on the inside. But let's talk about that one too. Did I question?
Is it a conductor or an insulator, that yellow part of the toroid?
Oh, that's nothing. It's air. So I guess it's an insulator. Yeah, yeah. At least in mine up here, it's air.
Yeah, okay.
Yeah, yeah. The ones that are passing around use, like I showed you, a core. Because the core, the atoms can switch in the same direction as the currents. And we haven't talked much about it this chapter. And I'm going to hold off till next chapter anyway. So that's at section 6 I said don't worry about for the test. That's what I'm going to use section 6 for the start of the next chapter.
Would it change what all of that was?
If it was what?
If it was a conductor? Obviously it would.
Well, okay, so if you put some material there, then the electrons that are in that material would, yes, have an effect on the magnetic field. In fact, maybe it's worth showing you again, since it's been a while since I showed you. If I were to take this, I can pick up no nails, right? If I turn on the power supply, it's a magnet, but I don't even know if it's enough to pick up one nail. I mean, maybe if I got it close enough. Yeah, now it'll pick it up. But if I then fill the inside with a core, then the magnetic field that is created from the current has an effect on the orbitals in the iron. They can align or de-align, actually, in some cases, but in the case of iron, they can align. And so the total magnetic effect is the effect not only from the current in this coil that we're calculating, but also the movement of the electrons in the orbital of the iron. And this can be 500 times or more electrons than in here. And so, as you saw, I can't pick this up, just fill it with a core, and you can pick a lot of them up. And so we can take advantage of the moving electrons, not just from the power supply, but the moving electrons that are in the iron itself. So, yes, that thinner, that yellow area, as you said, could be made out of something. And then if it is magnetic, it could be making it really strong. And that's why the ones passing around, you'll feel how heavy they are, because they're not just an air core like the one you'll do in lab. Yeah.
Can you explain again why the current is zero? The current going inside and outside.
All right, maybe now that I built this one, if I hold it up, okay, so imagine an Ampean loop on the outside. Okay, now I'm going to twist it this way. And as I look at the surface that's created by that Ampean loop, right here, these loops, current comes out and then goes back in from that loop. Here's the Ampean loop. I've got this section right here, let's say. Current goes to my right. Then as it goes to my right, it comes around and goes back that way, to my left. So no current. It goes out and then back in, and then out, and then back in, and then out and back in. So the total current through this Ampean surface is zero. Yeah.
And even if you did have a conductor in that loop, the magnetic field would still be zero outside that loop because the current's still zero.
Oh, yes.
It get stronger like you did with the
Yes, and maybe I didn't make that real clear. I think you're referring to inside. Inside, it's going to make it really strong. Yes, good point. But outside, still going to be zero. Right. Yeah. In an ideal setting. Yeah. So again, that's a neat property of these toroids, that there is no magnetic field on the outside. We've got it, as you'll see here, contained to the inside. So let's take the next step. The next step is to do what I call the interior part, the tunnel part of the toroid. Let's get in that tunnel and apply Ampere's law in that case. And so let's look at R that is now less than C but greater than B, what your author calls their loop number one. All right, so we are going to be greater than B but less than C for our value of R. And we can apply this Ampean loop. And so if I go the integral of B dot ds equals mu naught I inside, again, that first step is to take the dot product and look at the symmetries. And again, not exactly perfect, but the best that we can do, we will make this toroid really, really tight. And because of that, we will simply say that standing anywhere on this loop, the current distribution looks the same. That is, if I had, say, the tunnel going around this desk, and I stand in the tunnel, as I look at the current, maybe right here in front of me, the current's coming down. That means, I guess, right behind me, it's coming up. And then it makes these loops all the way around. If I move somewhere else in this tunnel, don't I really see the same thing? Don't I see current coming down, back up, and around? So whatever magnetic field is created at this point must be the same as this point. Now let me make it clear. I am not saying that the magnetic field here would be the same as if I took a step forward. Does the current distribution when I take a step forward look the same? I'd say no. I'd say it's coming over the top of me, but I'm really close to it. If I take a step back, then the current up here is really close to me. So please careful what I'm saying. I am saying that the magnetic field along the Amperean loop is the same. But I think there's a good chance that as I step closer or further, the magnetic field may change. So we'll see what we get. The nice thing about it, though, is that the integral is along the Amperean loop. So whether I am closer or further doesn't really matter. And we did the same thing when we did Coulomb's law. When we did Coulomb's law, we looked like at a charge distribution. And I used this pole again, and I said, I'm not saying as I get closer and further, the electric field can't change. But what I am saying, as I move along the same distance, and it wouldn't change. And so that's what we did then, and that's what we're going to do now. And so we should get B. And we wouldn't be surprised, I hope, at the end of this, if B did have different values depending on what R is. And we will see that. Same logic as before. Angle would be 0. And then it would be mu naught times the current that goes through our Amperean loop. Well, this side of the equation becomes B times 2R again. Or is it 2 pi C? Or is it 2 pi B? Or is it 2 pi little r? Yeah. And I don't even know why I'm asking it, just to save you paying attention, I guess. But yeah, hopefully it's pretty obvious. It's around the Amperean loop, which I'm representing with an R. The A, well, the A is this, but the B is this radius, and the C is this radius. And that's not when I'm doing my line integral, if I can say that word. I'm doing my line integral on the Amperean loop. It has a radius of little r. So that's definitely a little r. The other side of the equation is going to have us thinking again, how much current goes through the Amperean loop? Through the Amperean loop. See, here's an important difference between what we did a moment ago and what we're doing now. My Amperean loop is through the tunnel part of this. So the current that is at radius B, as it, say, comes out, or goes in, I'll just say out, as it comes out, doesn't that go through the Amperean loop? But then it arches over and goes back. Does it go through the Amperean loop? No. As it arches over, it is going back in the plane, but it is not going within the Amperean loop. And so in this picture, they're trying to say right here, this current, as it comes out, it's within the Amperean loop. But as it arches over and goes back in, this stuff here does not go through the Amperean loop. This loop is smaller in radius than C. So do we have current going through that Amperean loop? Oh yeah. And how would you label it?
I times whatever point you have.
Yeah, and so I being the current in each of those wires, and then N being what we like to say the number of loops, number of turns. How many loops do you have? How many turns do you have? And now you'll be able to see why the magnetic field from this structure can be so incredibly strong, is because we can wrap that many, many times, and that's what I wanted you to see when I was passing those around. So to finish up our equation then, we have this, that the magnetic field then depends on those factors. Probably doesn't surprise you that it depends on the current. More current means stronger field. Yeah, that's the obvious one. But the neat one here is it's the number of turns. And we can wrap that thing around thousands of times. And those ones that have passed around have thousands of turns. And therefore, the magnetic field can be thousands of times stronger than it was for just a single wire by itself. That's the neat part about this shape. So, no magnetic field on the outside. Strong magnetic field in the tunnel. Now let's look a little closer at the tunnel. Does it have the same value everywhere inside the tunnel? No, it doesn't. And as I was saying earlier, I kind of suspect that if I were to step out forward or step back, that it probably would change a little bit. There's the little r. Isn't that what the little r is saying? And so the magnetic field does change based upon what little r is. And so they've kind of drawn an Amperean loop that goes right through the center. But if I would have done the same calculation with an Amperean loop that's really close to radius little b, then in my equation I would have a little b. If I did an Amperean loop that was out here near this edge, I would have c, and B and C are a different value, so I would get a different magnetic field. So the magnetic field does change within there. Where is it the strongest? At C or B? Or in the middle? Isn't it the strongest when this is the smallest? And so as I come in, it gets stronger and stronger. And so if I were to be plotting the magnetic field from this toroid, putting the inner radius at B and outer radius at C, what I have so far is no magnetic field on the outside. Then once I get to the inside, I would have some magnetic field. And as I got closer to the donut hole, the magnetic field would go up in strength like a 1 over r squared value. And again, I'm hoping this is what you will see when you do the lab next week. You'll take your probe and go, nothing, 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 whoa, bigger, whoa, bigger, 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 and then we'll drill a hole in here so you can go inside the donut hole. And so what's the field inside the donut hole of all this? Bunch of questions, yeah.
So, as you go closer to the inside, isn't it less current interacting with the ambient loop, the loop 1?
No. As long as I draw an Amperean loop anywhere from as big as C to as small as B, the current that goes through it comes from right here. So I'm not going to see any change in current until I draw a loop that is smaller than B, which I'm about to do. But I haven't done that yet. So we've still got the third question.
But like if you're on the outside more, then you would go over it.
If I'm on the outside here?
No, like right at the edge.
Yeah.
So that there's more wire. There's more wire going over the ambient loop compared to the inside.
Oh, I don't care what goes over the top. The question is how much goes through. So if this is the surface, it can come up. It goes over all at once. That's not part of my calculation. I don't care about any current until it goes through the surface. Yeah.
I'm a little confused on what part of the wire itself you're getting the current from. Because if you have your loop, wouldn't C be outside your loop? If you went all the way down to radius C, wouldn't it just be between R and B? That's what I'm not seeing.
Wait. Say that again. I'm sorry. I didn't quite understand.
How you get current from radius C from the Amperean loop. Because isn't it the current that's inside the loop itself?
Yeah. Oh, okay, so maybe less than C?
R, B, R, and B, and then wouldn't go out to C?
Wait, are you trying to say that my ambient loop should not go all the way to C, but should just be a hair short of C?
No, I'm just saying, do you get current from all the way down at radius C?
Well,
Using that ambient loop?
the current comes from this red wire.
No, I see that. I'm just, I don't know.
And so,
It's actually relating into how the radius, normally in the calculations, if you were going to put the numbers in, you would do it from B up to R, which is
but no matter what ambient loop I draw, as long as I am in the tunnel part, so all three of those circles, the current comes out of the inside, arcs over and goes back in, but when it goes back in, it is beyond the ambient loop.
So you only take the current that's coming out towards
Yeah, you only take the current that is inside of the loop.
wouldn't be the current that's going in at radius C going in?
Yeah.
Don't calculate that.
And I don't, right.
That's what I
Right. That's why the inside current was the number of turns times I.
That's why I don't understand how you have it coming all the way down to C in your graph. If you don't have any current at C, is it right?
Okay. Thank you. Yeah. Oh, yeah, a bunch of questions. Yeah.
Oh, I was saying if you draw the point at C, it's an open loop saying.
Oh, now, of course, yeah, this is an ideal. So the reality of this magnetic field, if that's what's bothering you, is these are ideal calculations. The real one you will measure in lab, and you will see this thing go like that. You will see the transition as you go from, the current being close and far. Yeah. So that's the real world, and that's what you're going to see when you actually measure these next week in lab. Yeah.
Is this similar to what the coils we used in lab this week, and why they have like 90 turns or 72 turns on the coil?
Oh, exactly, right. We were trying to make a strong magnetic field this week in lab to bend the electron beam. Right, so we wrapped them around, depending on what model you had, 72 times or 90 times. And then we even had 2 of those stacks. Right. I wouldn't call those toroids. Yeah, they didn't make the donut shape. Yeah. They're the next one.
so for the N, like the number of turns on the coil, so you're just looking at inside R,
No, so,
R and B. So are you just looking at like the total number of?
yeah, so,
Those are the ones that are just on the inside.
well, the ones on the inside come to the outside, so
So it's all one.
it's all one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23 in this case.
So even though it goes outside the ambient loop, you still just count that as one.
Yeah. I'm really counting how many wires come out of my ambient loop. There's one here, one here, one here, one here, one here, one here, one here. That's my total current, yeah.
Toroid, about the same amount of current between toroid made out of 4 loops, so it's 1, 2, 3, 4, and then we're not made out of a million loops. You would still have the same magnetic strength in total, but it would be a different magnetic field density.
No. The magnetic field strength is based on the number of turns. Go with 1,000,000 turns and you'll get 1,000,000 times more than just 1 turn. For the same current. Now, you may argue that if I only had less turns, I'd have a fatter wire and then I can get more current. Okay, fair enough. Yeah. All right, well, shall we finish this toroid so we get to the solenoid here? Yeah.
You've never answered my question about what the loop 2 is. Is it supposed to
I haven't got there yet. Right. So now, let's do the donut hole. So here's the inside the donut hole. And so the third part of this toroid would be, what if R is less than B And again, your author doesn't give you a nice little loop there, but I wish he would, because when I draw an Amperean loop inside of my toroid, so right here, I'm going to, of course, get an integral on this side of the equation, which I won't even mess with. Let me jump to the other side. How much current do I have going through an Amperean loop that I've now drawn smaller than radius b?
0.
0. And so just like we did on the outside, we get a 0 magnetic field on the donut hole part of this. And so, finishing this graph, you should hopefully then see 0. And when you actually do it, you'll see a transition as you go from the donut hole in. And so your experiment, you'll see nothing, nothing, nothing. Then you'll see it increase almost dramatically. Then you'll see it increase with a 1 over r squared value. Then you'll see it drop off dramatically and be pretty close to 0 on the inside of the donut hole. Yeah.
That graph also means that if you decrease the distance between B and C, then you have a relatively constant magnetic field.
Right, so let's make sure we caught this. There's advantages and disadvantages to this. The huge advantage of this toroid is it can make strong, strong fields. Another good advantage is you can control where there is a strong field and where there are no fields. A disadvantage, or though maybe can be turned into advantage, is the magnetic field is not a constant value. It did change. And so there is a distribution. But as you're pointing out, you can make this semi-constant by moving B and C close together and maybe even move them out. And that big toroid, I don't know if you saw it, that was the whole idea. Who's got that big one? Hold it up there. See, that is a very short distance between B and C. And B is pretty far out there. And so that was the attempt to make a strong, roughly uniform magnetic field there. Yeah.
What's the point of the toroid if there's no magnetic field immediately outside and immediately inside, but only like inside the material?
Yeah, so you put something inside. That one comes out of one of those nuclear magnetic resonators from up in chemistry. And so you put your sample inside. Now, of course, what that really means then is you kind of have to separate the wires a little bit and run your experiment. But if you want to run your experiment in a location where there is a high magnetic field, you build your toroid like this. I can get it in there. And then, if this is my experiment, I place it in there. And I would get it in a very high magnetic field. Exactly. Yes. Yes. Yes.
What's the point then if we have something like the toroid over there where it's like a solid material?
Oh no, there's a well, that's kind of buried there, but they got a little hole cut out in there to get the magnetic material in there. Okay, but with all that said, there are other reasons we want a strong magnetic field. Not necessarily we want to put anything in there, but as we get started in the next chapter, we'll see that the magnetic field, just like the electric fields and capacitors, had an influence on our circuitry. This magnetic field can have influence on our circuitry. And so we don't necessarily want to get in there to get the magnetic field, but we want a geometry that has a very large magnetic field. We call these inductors, and I think you guys in circuits have already started working with the idea of inductors. We'll do that soon, but we want to make sure you have an understanding of magnetic fields so you can understand how the inductor works. But it is going to be related to the magnetic field.
When you make the difference between B and C, can't you make a tokamak from that?
Yes, this is a design of a tokamak. And for those of you who don't know what a tokamak is, the design here, and this is one of the examples I thought maybe I'd get to, but you have charged particles. And what's really nice about charged particles is they have a force only when they move perpendicular to the field. So if I had inside of this area a bunch of protons that are moving around, if they move this way, they will be moving perpendicular to the field. There'll be a force on them and they'll coil around in a circle. if they move along the circumference, they're moving with the magnetic field, and they have no force on them. And so these particles are free to move around inside of my toroid. As they try to leave, then there's a force on them circling them back around, keeping them trapped inside. And so that's the idea of the tokamak design, is to make a strong magnetic field in a circular pattern. The charges can freely go in a circle and they can move along, and as they try to get out of that circle, the magnetic field wraps them back inside. And so we'll have a problem like that in just a second. Let me show you the last design here. The last design is even simpler in design in this, and I'm never quite sure which is easier to show you, the toroid first or the solenoid. But again, in the lab that you are going to do next week, not only will you build a toroid, as I just said, but you will build a solenoid. You will take your metal wire, you will wrap them in coils, but instead of turning them around, making a little donut out of it, you will have something that looks a lot like this. And so here's kind of your author's attempt to say, let's look at a solenoid. If you, again, take this as a coil, his purple dots here are to indicate the direction of the current. And so he is saying down here the current goes down and then back up, down and then back up, down and then back up. And so right here, everywhere on, as you are looking on at the left, if I were to take my right hand and grab the coil right here, then the current would be coming out. We didn't grab that big coil, did we? No, that's okay. Let me hold this one here. But if I were to hold this up and think about the current coming out of there, if I were to actually grab this with my right hand, and I can't get all my fingers in there, but if I get maybe a couple fingers in there, you can kind of see that as my thumb points towards you, inside of the tunnel part, right, there would be a magnetic field pointing up. And you can do that for anywhere on the coil. And so as the current coils around here, we are going to get fields that add up in the tunnel parts. And they're going to add up to be pretty strong. Outside of the tunnel, out here, you would get, say on this side, a magnetic field going down from that wire, and down from that wire, and down from that wire. But this wire would make a magnetic field going up. And so there's a cancellationing happening over here. And same thing on this side. And so, like the toroid, the solenoid has a nice effect. What's going to happen is you're going to get a really strong field in the tunnel part and very weak field outside, which is again why in the lab you are asked to build one of these and take your probe and go measure, 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 whoa, measure, 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 get on the outside, whoa, measure, 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 measure. And so you are to see the transition of the outside to the inside and the field strength on the inside versus the outside. Yeah.
So is that how, what is it used for, like shooting particles or?
Well, anytime you want to make the field very, very strong. This one, I would say I just want to use it to simply lift something up. Not lift something up. So I just want to make it strong enough to maybe lift crushed cars at the junkyard or the recycle plant, so I can pick them up and drop them into the furnace and move the chunks around. This one here, might as well show this one to you now, is a nice solenoid. Unfortunately, you can't see the 10,000 wires that are wrapped in a circle, but I'll just mention it before I even do the math, is that the strength of this solenoid is going to be connected to how many turns you have. Okay, and in this case, we have 10,000 of them wrapped inside of here with a core. The reason for that is on the outside I have just two D-cell batteries, 1.5 volts each, total of just a lousy 3 volts. But without any current on, it's non-magnetic. As soon as I turn the current on, just like those nails, it should be very magnetic. And it sticks. And in fact, let me turn it off to show you it unsticks. But it sticks the most when I get it just aligned right. I'll turn it on. And so this is significantly stuck. And there's no pulling this thing apart until I turn off the current. And then it just falls apart here. And so that's one example. You probably see it on a daily basis of what if I just took a solenoid like this, dropped in the middle of it a magnet. If I turn the current in one direction, it would pull this down. If I turned it the other direction, it would push it up. If this is the lock on my door, I just have to push one button to make the current go one way and my door's locked. I push another button on my remote, the current goes the other way and my door unlocks. And so, oops, there's the kind of the idea of the magnetics. And I have heard numbers as high as there's over 1,000 magnets on your car used to move things. Your starter motor is another great example. You put that key in, and you probably don't think much about it. You just turn the key, right? But that key does not actually start the starter motor. What that key does is go to a small solenoid like this. The purpose being that it can make a metal piece go up and down. That metal piece, when it goes up and down, is what makes contact for your starter motor. Because that starter motor is going to need about 300 amps. And it's not considered safe to have a switch that you're going to touch with your human hands with a metal key with 300 amps nearby. Because when something goes wrong, it goes really badly wrong. And so instead of having 300 amps near your hand, or even for that matter just in the passenger compartment where a fire can start, you're much better off to use the key to control a solenoid. Then the switch that actually goes to the starter motor is in the engine compartment. And when something goes wrong in there, of course we also have fuse links to make sure that we don't get a fire, but if those don't work, then we have a fire in the engine area. And there's a big firewall between the engine compartment and the passengers, and hopefully everybody gets out safe long before the fire ends up into the passenger compartment. Then, besides that, not only is that current going to make the starter motor go on and off, but that same current then goes near another solenoid where they have a gear, where the gear then gets pushed into the flywheel, so that when the starter motor goes on and the gear of the starter motor goes around, it can turn the engine. But as soon as you turn your key back from start, the current goes away and the gear, the little pinion gear from the starter motor, backs up. And now the engine runs on gasoline and the starter motor is now disengaged. Once in a while, hopefully this hasn't happened to you, but you ever accidentally turn it to start while it's running? And what happens is when you turn it to start is you have now put current to this solenoid and it pushes the piston or the pinion gear into that flywheel. Well, the flywheel's already going around. So what do you hear? You hear this grind, right? You turn it and you go, you know, and hopefully your first reaction is to let go of the key before the do any damage between those two gears that are trying to engage, one not moving and one already moving. So you don't want to try and start it while it's already started. Anyway, I didn't mean to spend quite that much time, but there is thousands of good examples of using magnetism in our cars around us. And so more than anything else, the world we live in is electro and magnetic. We can't understand computers, we can't understand the operation of cars, we can't understand the operation of sensories until we understand electronics and magnetism. It's the world we live in, and for good reason. All right. Well, let me change this picture because this is maybe a more realistic picture. Here is your author's overly idealized solenoid. And so just like we did with the toroid, let's take the liberty of taking some real-world applications and calculate an approximation to them by saying, well, what would happen in a perfect world? And here's what I mean by a perfect world. You can see in my solenoid that I actually have spaces between each loop, right? What would happen if I got them really tight together? And if I got them really, really, really tight together, they might look a little bit more like this. This is your author taking a cross-section where the current comes out and goes back in, comes out, goes back in, goes out, comes back in. And so this is the current coming out, this is the current going in. He's just drawing a cross-section of it, but what he wants you to see is inside there is going to be a magnetic field. There's going to be a strong magnetic field. We should be able to calculate it using Ampere's law. So let's give it a try. And so Ampere's law applied to this solenoid would look maybe something like this rectangular loop. So let me take that rectangular loop there. If I apply Ampere's law here, I've got an integral of B dot ds equals mu naught times I inside my Amperean loop. You will notice, since I have a rectangle, it's probably best to call this Section 1, Section 2, Section 3, and Section 4. So there it is, Section 1, Section 2, Section 3, and Section 4. And so this closed loop has 4 pieces. Okay? Now, if I look along section number 1 here, 1, and I go B times ds times cosine theta, the argument goes something along this, that if you were to stand anywhere along section 1, the current distribution would look the same. At least it would look the same if this solenoid was infinitely long. And so, again, overly simplifying it because we don't ever really have an infinitely long solenoid, nor do we ever really have them infinitely tight, but that's a good first step. All right? And so treating it that way, I would say that if I were to stand here, I would see current to my left and right, and it would look the same back as forward. But if I were to move further over on the solenoid, since the solenoid's infinitely long, or at least very long, the current distribution would still look the same. And so my argument is, like most of these Amperean loops from symmetry, that my magnetic field is the same, and I got to pull it outside my integral. And as long as we're in passing, if it's not, I got to leave it in my integral, right? Fortunately, I could apply things like Stokes' law to these integrals and still do them, but not this semester. But that's why you guys are learning how to deal with these more complex vector calculus ones so that we can do the more realistic problems next semester. Or I shouldn't say we, I should say you, because you'll be there or whatever university you're at for the next level. All right? But in this case, I'll just put the B on the outside, and then I'll just have the ds. The angle here is 0 degrees. The next one, step 2, or section 2, is going at a right angle to the magnetic field, at least the part that is on the inside here. And so by similar design here, I would say then that the angle is 90 degrees. Whether there is or is not a value to the magnetic field really is not an issue here. For section 2, it's all about direction. And so I would argue that, again, by symmetry, when I am outside, it's got to be perpendicular to this. That argument again comes like we did with Gauss's law. If it wasn't perpendicular, then what we could do is we could imagine this whole solenoid and flipping it around. And if it was, say, pointing off at an angle, when we flip it around, now the magnetic field points up instead of down. But yet we have the same current distribution, which wouldn't make any sense. How could we possibly get a field that is different when we have the same current distribution but opposite in direction? What we should have is we should have the same field but opposite in direction, and that's only going to work if we have a magnetic field that is perpendicular to this. And so whether it is on the inside or the outside here, you flip this solenoid because of the symmetry argument, again, like we did with Gauss's law, you've got to have it perpendicular to section 2 and section 4. And so both section 2 and section 4, whatever the strength of that magnetic field, inside and outside, I don't know, and I don't care, I just know it's 90 degrees, because what's the cosine of 90 degrees? It's 0, and so that's enough to do those integrals. That's going to be easy, yeah.
Do we purely choose a box that's going edges 1 and 3 are parallel with the magnetic field for convenience? Just 2 and 4 are 0?
Oh yes, absolutely. Remember, remember Ampere's law is good for any closed surface. So if draw a circle, fine, but it's too complicated to do the integral. So get away from that right away. You know, go to something that's going to make it easy to do. And so just like we did with Gauss's law, the trick is finding the right Gaussian surface. The trick here is to finding the right Amperean loop. And usually the right Amperean loop has the same symmetry as the current. And these are kind of rectangular, boxy currents. So I have kind of rectangular, boxy loops. Before I had circular current, so I had circular loops, right? Now, number 3 can be kind of argued one way or another here and say, well, what is 3? I'm going to take the cheap way out and say 3 is infinitely far away. What's the magnetic field? 0. Okay, good. And so we can come back to the outside here in just a second. Actually, I would rather do some examples here. But you're going to get a 0 there. And so those 3 sections, 2, 3, and 4 come out to be 0. The only one significant really is number 1. What does that have to equal to? I times the current on the inside. How much current is on the inside? Well, why don't we call I the current in one loop? And so as you look at this Amperean loop, doesn't it come out here and go in there? So there's 1, there's 2, there's 3. The stuff that comes back out doesn't go through the Amperean loop, so I don't have to subtract those off. But the stuff that goes through the Amperean loop is really how many turns are within my Amperean loop. So I'm going to write this as n times I, but I want you to catch that the n here is a little different meaning, because what did the n mean with the toroid? The total number of loops in my toroid. Is that what I mean here? No, I mean the total number that is within the length L, don't I? Yeah. So let's do this. So we don't get ourselves confused, let's not write it as a capital N. let's write it as a little n times L, where the little n is what we would call the turn density, the number of turns or the number of loops per length. Otherwise, I would be tempted to count how many turns I have. Although, the truth is, to get the turn density, what I'm going to have to do, which you will do in the lab next week. You will count how many, get the meter stick out, measure how long it is, divide those two, and get little n. So you end up counting how many turns there are in the whole loop. But to help keep it straight between the equation for the toroid and for the solenoid, we like to use a little n here. So this side of the equation then becomes just B times L, because that's the length of section number 1. An L shows up on both sides of the equation, and so when it's all said and done, I get mu naught times little n times I. And so there's our last equation I wanted to get to for the solenoid. What is the field inside the solenoid? And if you'll let me cheat a little bit, so we can do at least a few examples before we leave you for the weekend, and maybe we'll have to do some more on Tuesday and start the next chapter a little bit late. We'll kind of play that by ear, but let me cheat and say, anybody want to make a guess on the outside? 0. And so outside would be, or could be, 0, and let me just say it's 0, and so we would have a plot of the magnetic field. If we call x equals to 0 the center of our toroid, and r the radius of our toroid, solenoid, then outside we get 0, outside we get 0. That's a nice feature of solenoids, just like they were for toroids. Inside, we get a very strong field. Again, another nice feature, strong field. Maybe not quite as strong as the toroid, but certainly very strong. But there is a nice added feature inside this solenoid that I want to make sure you see. What is that? It doesn't matter where I drew the line for section 1, did it? I could have done it here and end up with the same thing. And so what I will find is that the value of the magnetic field is uniform, which was kind of your approach of trying to modify the toroid to make it uniform. But if you really wanted it uniform, build the solenoid. The solenoid will make a nice uniform one. When you guys do the experiment next week, you will measure this. You will measure 0, 0, 0, 0. Let me do a different color. 0, 0, 0, 0, 0, gain, kind of uniform, and like that. And so you'll be seeing what measures in the real world, noting that our approximation is not going to be exactly the same as what we calculate, but you are asked in the lab to make a plot of what is it theoretically and plot it, what did you measure, and see the two on the graph. Same thing with the toroid. You are asked to make a plot for what theoretically it should calculate out to be, and then experimentally and overlay them on top of each other and see how close our theory is to our experiment. And it's reasonable, but not that close. All right, so I've done a lot of maybe more theoretical ones here. Let's put this into practice. And problem 4 is the first one I have on my list. It's one I showed you at the end of last time. Is could you get the magnetic field in the center of this little wire that makes a ring? Well, let's read this here together. It says, a conductor consists of a circular loop of radius capital R and 2 straight long segments as shown in the figure. The wire lies in the plane of the paper, and the current is I. Find an expression for the vector magnetic field at the center of the loop. And so this is a good one to get started because it goes back to our B-ups of art, but it also means we don't have to go back and rederive those same equations. Didn't we already do a loop? And what equation did we have for a single loop? Anybody remember? Mu naught I over 2R. Wasn't that the equation at the center of the loop? Was the first one we did? Or was it the second one we did? First one. It was the first one we did. Okay? And again, let me not take time to rederive it. But you could go through and start with B-ups of art. You could go through the integral. That's what you're going to get from a loop. So I claim that the magnetic field at the center will be partly made from this loop. But that's not the whole thing. What else is going on? Yeah, you might say I have an infinite or semi-infinite wire to here, then a loop, and then another semi-infinite. But what about the two semi-infinites? What would those do? That would be like just one wire, right? And so you can really hopefully say that I have a combination of these two. I will call this field number 1 and field number 2. And now maybe I should ask, what's the equation for the magnetic field from a long straight wire? Mu naught I over what? 2 pi R. They almost look the same. It's a perfect recipe. There's so many things that look the same in this one. You just be really, really careful with them. There's so many different ones to look at there. All right, now the total field then is going to be the sum of the two. And so the total magnetic field, and it is a vector, means that I have to add the two fields together. So number 1, I have to know its magnitude, and number 2, I have to know the direction. So let's look at the loop a little bit carefully. You already gave me the equation for the loop. Let's figure out direction. So what direction is the magnetic field in the center of the loop from the loop? Yeah, right hand, curl my fingers around, my thumb is pointing in. Let's call that the negative z direction. So number 1 would be mu naught times I over 2 pi r, where r is the radius of the loop. Let me come back to the problem because he said considered a circular loop of radius capital R. So okay, so I can use the same symbol up there for this problem because he says use capital R for the radius. The direction would be the negative k hat direction. Calling that into the screen. The other field is mu naught I over 2 pi. Oh, and what's this R? Okay, it's the distance from the wire, which in this case it is, it's the same, isn't it? And so they've kind of given me a case where it starts here and the distance away from the long wire, the perpendicular distance away, is R. So yeah, they do come out to be the same R for that case. I can imagine them changing it up and it doesn't come out to be the same. I mean, some crazy professor would probably make it on the test that way, so just to see if you're thinking. But I don't know who would do that. Okay. And what direction would it be? Well, again, just looking at the wire, I'd grab my right hand, grab it, put my thumb in the direction of the current. My fingers would curl around in this way. And so on this part, which is below the wire, my fingers are going into. So in this case, they are the same direction. I suppose if we somehow made the current go in the other direction, they would be in that opposite direction. And so some crazy professor would probably make it that way on the test just to see if people are paying attention. I don't know. Okay. And so what you end up with is a negative 1 plus 1 over pi, is that it? Kf. And so there would be the total magnetic field. Both of them are into the screen, both of them are a distance r away. A good first step. How about another one? What if I did number 5? 4 or 5? Where's the big one? Right there. Well, let's read it together here real quick. Number 5 says, determine the magnetic field at point P, a distance x from the corner of an infinitely long wire that has been bent at a right angle as shown in the figure. The wire carries a current I. Okay, so they want me to find the magnetic field. Now, of course, the magnetic field would be at what position? Okay, so they say point P. Now, I can think of this as a magnetic field being created by the first part of the wire, which is the part coming up, plus the magnetic field created by the part that is then bent and going horizontal. In fact, why don't I start there? How much magnetic field do I get at point P from the wire that is going across horizontally? Yeah, we talked about this one, right? This is when you do the cross product. In B-ups of art, the ds is this way, the current is this way. So the angle between them is 0, and of course that gives you a value of 0 when you do the cross product. So the magnetic field at point P is all going to be created by this wire. This wire is not going to create any. So that kind of reduces the problem from being the 2 wires down to 1 wire. And so now what I have for number 5 is I have just 1 wire, and I'm looking at the point P, a distance x. All right, well, how do I get the magnetic field from any straight line segment? What was our formula for that one?
Can you just divide the long wire by 2?
Fair enough. In this case, I can divide by 2. But I do want to ask that question. What is the equation from a wire section in general? Mu naught I 4 pi r. And this is the derivation we had last time. We can either talk it about cosines or sines. Does anybody care? Should I do the sine since that's the way it's in your book? So sine theta 1 minus sine theta 2. The picture we had in class and the way we derived it was if point P is up here, then measuring back to here is theta 1, measuring out to here is theta 2. And we have to think of theta 2 as being negative, as we talked about. So let's apply that equation, 4 pi, is that right? Yeah, 4 pi. Let's apply it to this scenario. So if you imagine kind of picking this up and moving it over to here, where maybe I'm moving the point P to here, then I guess I would ask, first of all, what is theta 1? Well, I guess going out that way would be theta 1. So isn't theta 1 0? Although also if you flip it the other way, you could call it 90. But one of them's got to be 90 and one of them's got to be 0. But the way I'm thinking of it is I'm thinking of this point here and then shifted to here. And so this point P being here means that that angle 1 gets smaller and smaller and smaller, and so I have sine of 0 degrees. It also means that theta 2 becomes 90 degrees if this goes on forever. Now, nothing goes on forever, but you know, if it goes a few centimeters in a microprocessor, this could be 89.999999 degrees. All right. And so I would put sine of negative 90 degrees. Either way, that comes out to be 1. And so the magnetic field, at least the strength of it, not direction yet, but at least the strength of it, just reduces to that. Which, in the symbols we have up there, the distance away is labeled as an x. And so I will finish the problem by, well, I guess not quite finished, I need direction, but I'll finish the magnitude of the problem by putting an x in there. And so this would be it. And as you pointed out, that would be half of an infinitely long wire. So we could have stayed even away from this and just said, if this is the equation for an infinitely long wire, start there, take half of it. And we would have had it. But I wanted to see something more general, that I could actually then get the magnetic field anywhere, right? I could put P right here. Could you get the magnetic field here? I mean, you'd have to give some dimensions in there, but yeah, you would have theta 1. And you would have to have, well, theta 2 would still be negative 90 if it's infinitely long. But would make this problem harder if we were here. Wouldn't we get an effect from that wire? So we would have another theta 1 and another theta 2, which again would be negative 90 for the theta 2. But we would have to consider the magnetic field from each of those at that point P. And we'd probably have to go through a little geometry to find those angles. But at least in principle, I hope, you could now find the magnetic field anywhere on there, right? In fact, better still, I bet, and I guess I will be betting in 7 days, that you could find the magnetic field anywhere in that plane for any configurations of lines and arcs. No matter how complicated it is, right? Just a bunch of angles, find the angles, and put it in. All right, well, let's finish it by saying direction. What direction is this magnetic field? Yeah, and so again, taking my right hand, grabbing the wire with my thumb pointing out, realizing my fingers are wrapping around this way, I get into the board. And so to make it a vector, then I get a minus k hat direction for the direction of the magnetic field. And so the magnetic field goes into the board. Oh, good. 2 minutes, enough to do another one. Look how fast these go. Man. It'll take you like minutes to do your homework. I'm kidding. But I did want to make sure I got a chance to do at least a few of these, because again, in case you missed it, we did a bunch of circular arc stuff and a bunch of straight lines, and as long as everything's made out of that, or solenoids, or toroids, or wires, we got all those. Just take what we have and put it together, and that's what number 8 is doing. Since we only have 2 minutes, I'll read it kind of quickly here, but there's the picture of number 8, and it simply says, a long straight wire is carrying a current I. A right angle bend is made from the wire. The bend forms an arc of a circle of the radius shows. Determine the magnetic field at the center of the arc. All right, so again, we know how to get the magnetic field from an arc. We know how to get it from a wire. We know how to get it from a wire. Maybe we'll do direction first on this one, since we just got a short moment to do. What is the direction of the magnetic field at this point from that wire up there? Into the screen. How about the magnetic field for this part? Into. How about from this part? Yeah, now this is the part where the rolls of our fingers and thumbs switch. Now I'm going to put my fingers in the direction of the current. So I curl my fingers in the direction of the current, and my thumb gives me the field, which is, again, into the board. So for straight wires, put your thumb in the direction of the current. For curved wires, put your fingers in the direction of the current. Okay? But fortunately, they're all into the board. And so adding up three vectors that are all in the same direction is nice. And so the total field here would be the first one plus the second one plus the third one. And in fact, look at the first one. Isn't the first one just a wire that, or a semi-infinite wire? Isn't that the one we just did? Where it would come out to be a mu naught I times 4 pi in the distance away, which in our notation for this problem is little r. And so that would be the magnetic field from the first one. Likewise, that would be the magnetic field from the second one. Because again, it's a semi-infinite wire and the arc goes along here, and from here forward it's infinitely long, so theta 1 is 0 and theta 2 is 90 degrees. The other one is a quarter of a circle, and so the magnetic field from a full circle was that, and so I will do a quarter of a circle and done with problem. And we still have 15 seconds to spare. Shall we do the next? No, I guess. All right. So good luck working on that. I know Don's going to be helping you on Friday, and we'll have the review on Sunday. More examples on Tuesday.